So here's one example of a dihybrid cross that Mendel performed. He had pure breeding lines that differed in two characters now instead of just one. Yellow seeds with white flowers, green seeds with purple flowers, both of them pure lines, and when crossed together he observed an F1 that produced yellow seeds and purple flowers. And this F1 he surmised was a dihybrid. Now, what else can we conclude? Well, we've seen the yellow versus green seeds before, so let's use the same symbolism that we used before. So, with the allele that gives the yellow characteristic dominant to the little y, giving us the green phenotype, and then big Y with a dash giving us yellow. Now for purple versus white, in the F1 we see purple flowers. So I'll define a new allele as P dash giving us purple and little p giving us white. Now this does assume that these are different loci, that they are alleles of different loci. If in fact that was not the case, we would see something in the F2 that we'll understand later. We would fail to see any wild type phenotype in the F2. Now, we haven't discussed yet which is the wild type phenotype, and it's a bit arbitrary here, but we'll see what we mean in a moment once we start talking about the different outcomes. So Mendel went on to self the F1, meaning an F1 times F1 cross, in order to arrive at an F2. So we might ask ourselves the question, assuming that we are dealing with two loci, and assuming that those loci are independent of one another, what might we expect in the F2? First off, we might ask the question, well, what proportion will be yellow? Now we've seen this before with a yellow times green to give us an F1 yellow. When we self that, we see a 3-to-1 yellow to green. So again, we would expect to see a 3-to-1 yellow to green. Now, we've seen that the purple phenotype shows up in the F1. We've defined these alleles. I should have also made this part of the definition to say that this allele, the big P allele, is dominant to the little p allele. We would also expect to see a 3-to-1, therefore, of purple to white. Now the question becomes, how, if these two loci are assorting independently, and we'll learn about assorting here in a little while, what we mean by that specifically, but if these two loci are independent of one another, we can ask the question, if we have these two independent 3-to-1 ratios in the F2, what actual phenotypic ratios might we see? And we can do this using requirements, very much like what we do for pedigrees. We can ask, well, what are the different possible outcomes and what's required in order to get that particular outcome? So we could say, what would be the probability of getting a plant that is both yellow and purple? So yellow seeds and purple flowers. Well, what's the probability of getting yellow? Well, this has a probability of 3/4, and the purple also has a probability of 3/4. So because we say and, we would multiply those two together. So taken together using the product rule, we would end up with 9/16 is what we would expect for purple and yellow. We could also ask in the F2, what's the probability of getting yellow and white? So yellow seeds and white flowers. The probability here, again, is 3/4. The probability of white, this is the 1 in a 3-to-1 ratio, so it would be a 1/4 probability. And because we say and in between there, we would multiply these two together as well. So this would give us a probability of 3/16. We could then ask what's the probability of green, and let's do purple flowers. So this would have a probability of 1/4, and this would have a probability of 3/4 to give us another 3/16. Okay, so the last remaining one, where can we find some room to do this? Let's go in here. The last remaining one would be green seeds and white flowers. These each have a probability of 1/4, assuming that they're independent, as we've been mentioning, and because we say and, we would expect a frequency of 1/16 for that category. You may have encountered previously what's known as a 9:3 to 3:1 ratio. A 9:3 to 3:1 ratio, which is what we've just been talking about here, 9, 3, 3, and 1, arises as two independent 3:1 ratios, that are combined essentially. We now have two independent 3:1 ratios that are combining to give us this 9:3 to 3:1 ratio.